click here to open the thing to get the link. Here's the link. Let's post it to our magical meetup. Actually, it's not to the meetup, it's to something else.
Etherpad.
Etherpad that I don't have open. That guy. And
You can post to Meetup too.
oh, I should have posted it to Meetup. What am I doing?
That way people are on this Meetup site.
Here we go. There's our live stream. All right, back over here to sockets and requests. So, as everybody here knows, I'm David Ernstrom. I'm giving a brief presentation on sockets and requests. And it looks like my bottom part of my slide's cutting off on the web stream, but that's all right. We'll make do. Sockets and requests, that's actually two different topics that we're going to kind of merge together. Socket communication is essentially communication from one computer to another computer. Okay. Background on me, everybody here locally knows, but I have been a Python software developer since 2006. Just hit my 10-year anniversary at DuPont. I grew up in the Davis County area. I moved to Logan in 2001 after a religious sabbatical to British Columbia. Try and fix this on the live stream because it's not digging it. Sorry guys. There we go. We'll do that. I graduated from USU with a Bachelor of Computer Science, Bachelor of Computer Engineering, and a Master's in Business Administration. DuPont makes holograms, and that's where I work. They're sponsoring my attendance here and some of the things that we do here. They have been a sorry, should have done this already. My little notes here. Let's get that over here. They're the world leader in photopolymer holography. We're in the security and authentication industry, specifically protecting brands against being counterfeit. So we put our holograms on their product. We put serial numbers on those holograms. We can track those serial numbers as they move through the customer's supply chain, and also as the product enters into the marketplace. We have overt and covert security features on our holograms so that we can then determine if product is counterfeit or legitimate. Our code base is almost entirely Python. We have, as of this morning, 44,401 lines of code. And my PyLint score as of this morning was 7.28. My target, no, it's up. That's up by one since a couple months ago. My target is 8, so we're getting there. So what are sockets? I don't know if anyone's familiar with this OSI model. Anyone want to give a 1 minute on what the OSI model is? Anyone remember the OSI model?
Different layers of networking.
Okay.
You've got your hardware level, which is your cables and connectors. Your framing level, which is how you put signaling over that hardware. You've got an addressing or link control layer, which is how you get packets from one point to another. You've got a layer that can handle reliability, and that would be your transport layer.
Transport, yep.
And then session is like, it's like when you do a TLS handshake, you've created an encrypted session that lasts over multiple requests.
Okay.
And then presentation and application. Presentation, these two are a little bit fuzzy, but presentation is mostly that we transmit 8-bit bytes that tend to be interpreted as ASCII or UTF-8. application at that level, you're looking at stuff like HTML is what you're transporting, and what is the semantics of
Correct.
that.
Correct. So at each level, you're essentially abstracting the details of the previous level, making it a little bit more higher order, a little bit easier to comprehend what's actually going on, so you can think about it logically rather than the nitty-gritty details of whether you're sending ones and zeros over the wire. So at a socket level, the socket implementation is what abstracts the transport layer to the session layer. A socket on a computer specifically creates that connection to another computer using TCP or UDP. I don't know, there's probably others. And that allows you to not have to worry about, did the other computer get my message? And those kind of details are abstracted away from you having to deal with that. The two primary types of sockets that we typically work with are TCP sockets and UDP sockets. The bulk of them being TCP sockets. TCP sockets are, as I said, you can expect that the receiver is going to get them, because built into the TCP protocol is that handshake, that guaranteed delivery, so that when the receiving end gets the socket, there are certain acknowledgments that are sent back saying, hey, I got the message, and then you end up acknowledging the acknowledgement to let them know that you got that, so they don't have to keep on resending that to make sure you got it. So it's very handy. Specifically, I'm talking about Python sockets. So there's some code to look at, and this is code that I've taken right out of my Python code base over at DuPont. Import socket. You create a connection calling socket.socket. You pass it. Oh, I cut off. You pass it a couple parameters. The most important is that second parameter, the one that got cut off. You're telling it that you're going to make a TCP socket connection. At least that's what this example is. It's a TCP socket. I set a timeout on my sockets of whatever number of seconds I want. And then we go ahead and run the connect call, which allows us to connect to another computer's IP address at a specific port. Between the connect and the shutdown, we have some meaningful stuff that we want to do, and that meaningful stuff takes the form of sending data and receiving data. Following which, when we're done, you issue a shutdown command followed by a close command. Now that shutdown command and close command, there's a lot of kind of discussion out in the community of which ones you need to do and which ones you don't need to do. The textbook answer is that you should send a shutdown command letting the other end know that you're about to disconnect, and the parameter is saying what ends of the socket you are interested in closing. Typically, right before a disconnect, you want to shut down the read end of the socket and the write end of a socket, and you're letting the other end know that. However, you might have a scenario where you want to let the other end know, hey, I'm done writing, but I'm going to hang out here and listen to more stuff that you might need to send to me. And so you might issue only one end of that if that ends up being the case. Following which you issue a close, and that lets the other end know that you're done, and then they receive that you've disconnected. My little notes screen kind of went away. Let's try that again, see if it comes back. It doesn't. That's all right. We don't need notes. Here's an example of the meaningful stuff that you might do on within a socket. One of them being a receive. Now, it used to be that when I would do a receive, you would just see that self.handle.receive length. But as my code has matured over time, as I've learned more, I've kind of tacked additional pieces onto this kind of receive. This .decode UTF-8, if anyone's was here for my Unicode presentation, one of the things that you want to do as soon as you get data coming from the other end, that data is transferred in bytes, you want to immediately turn that string data into Unicode. And so if you've negotiated with the other end of this data, or of this stream of data, that you're going to be passing ASCII text, or you're going to be passing some bit of text, as soon as you receive that, you're going to want to flip that into Unicode.
That depends on the protocol. You can have a binary protocol, but like even HTTP, it's Latin 1 by default until
Okay.
you see a header that says it's something else.
Okay, yeah, sure. The point, though, is you know what the other end of the you need to know what the other end of the socket's going to send you, and at that point you want to flip it into Unicode as best practice as a Python developer. Now this is a little bit tricky from what I would typically do. I kind of shortened this code because you might not necessarily want to transfer it to Unicode until you know you've gotten the entire message, because this receive call might not send you all of the data that the other end of the socket was trying to send you, and you don't want to flip that to Unicode until you know you've gotten it all. So typically what you would do is you would negotiate with the other end of the person you're talking with. You'd negotiate maybe that the first byte of data is going to demonstrate is going to be a length. So they're going to tell you how many bytes of data they're going to send in this transmission, and then you will continue to receive until you've received that number of bytes. The other thing that you might do is come up with, negotiate out some sort of a delimiter, so some sort of a terminator signal. Maybe it's two carriage returns back to back, or maybe it's this string of 10 magical characters that you guys have just decided, hey, I'm going to send this at the end of every transmission, and if once you get that, you know I'm done. So once you get that, you flip it into Unicode, and then you're able to receive, or you're able to deal with that data on your side. The other really important piece that I've just recently been building into my infrastructure is this select call. What this select call does is it, at an operating system level, you're able to check the sockets and find out if there's data to be read, or if there's data to write, or sorry, if the socket's still open to be able to write it. And then I can't remember what the third option is. And then the fourth option is how long it should go before it times out. The idea being that you make this select call, you pass it a list of sockets that you might want to write to, you pass it a list of sockets that you might want to read from, and a third list, I can't remember off the top of my head. And then what you get back is a list of those that are readable and those that are writable. And you can see here I'm only interested in receiving, and so I'm throwing away the other ones by storing them into an underscore parameter there, because I really don't care the data, I'm just going to throw it away. What I am interested in is, are there any items in this list that comes back called readable? And if there are, then it will pass through and go ahead and receive that data. What I kept running into was the other end of the socket would drop the connection, and then I'd be deadlocked because I didn't have a timeout set, and my system didn't recognize that the other end was dropped. And so I needed to deal with that. So that the proper way is to run that through the select function call like that.
You can also set the connection timeout.
Yeah, and I did that on the previous screen. You'll notice that. Right there. Connection.set timeout. Here's an example of passing binary data. One of the things that I talked about is, okay, well, if I don't know what the terminator looks like, or I'm passing binary data, like an image, like this example, what I negotiated with the other end of this socket was that the first byte was going to represent how many bytes of data they were going to send me. And so I used a Pythonic struct right there at the top. I told it that it was, all of my code is Unicode. So the very first thing is I'm saying that I have a byte to define what the struct is. The greater than sign says that the data that I'm going to get is big endian. I'm not really going to get into endianness, but that's something you need to be aware of. If you're on, let's say, a Windows machine communicating with a Linux machine or something like that, you need to be aware of the endianness of the binary data that you're going to be transferring. And I said that I was interested in receiving an integer out of that, which is 4 bytes of data. I set my timeout to 10 seconds for this particular instance. I read 4 bytes into my buffer, and right here I ran unpack from my buffer, took the very first element I got back as being my packet length, and then I would continue to read until I received that packet length's worth of data. Once I got all of that data, then I knew that I had my image, and I was able to pass it into the pills image.open, at which point I had an image that I'd received from the other end.
Question.
Yeah.
This is kind of ties to ZeroMQ stuff. If you've got a huge image, say larger than your memory size, how does that work?
A huge image larger than your memory size?
Yeah.
What if you look at the slide? So this socket.readAll, that's a function that I've written internally.
Okay.
What it does is it continues to read using this receive function.
Okay.
It will read over and over and over this 1024, and I just keep on appending it to, actually I append it to a list in my function until I get something that's that long.
Okay.
So each receive doesn't give me the whole thing, but through continual iterations of the same thing, it continues to build that into memory
Okay.
until I'm
So it's
satisfied.
streaming, basically.
Yep. Yeah.
So are you taking, if your data stream is longer than 4 byte integer, in other words, the equivalent 4 byte integer,
Uh-huh.
which is pretty big, but still, if it's bigger than that, are you reading multiple blocks? to
No,
achieve
because I know that he's not going to send me an image whose length is bigger than that 4 byte.
Okay, and if you did, you'd have to make accounts for that.
We'd probably just say 8 bytes. You know, and so I would just read, okay, the first 2 represent the
But
size.
my question fundamentally is there a practical limit to what you should have in your, or are you just using 1024 as your buffering size?
The recommendations are to use a power of 2.
Okay.
Something that's practical. You start getting into the way I
I
understand
mean, I wouldn't
it.
want to try to transfer a terabyte in one shot.
Yeah, the way I understand it, you start getting into how does that 1024 overlay into, what do they call them, packet sizes and stuff like that. Really the nitty gritties beyond like why a power of 2 and stuff like that, I don't really understand so much as everything that I've always seen kind of just suggests 1024 is a pretty good number to use. You just use it. Anyone else have any better comments than that on the topic?
1024 is 1K, that's fine.
With larger numbers, you'll be calling that function less and having less overhead. With
Yeah.
smaller numbers, you have a lot of function call overhead, and it just kind of like washes out somewhere between 1 and 16K for most applications. So if you get anywhere in there, you're doing great.
Okay. Now, I do have a scenario where I'm looking for a specific delimiter, and I'm receiving little tiny short sections of data, and I receive that 1 byte at a time.
Okay.
And so that as soon as I get the delimiter, then I let the socket act as a buffer, so that I don't have to buffer it locally.
Yeah.
As soon as I pick up that delimiter, I can go on and logically process it, and I know the very next call to that receive is new data
Well,
to deal with.
that's kind of like ancient asynchronous chatting, which you finish your sentence with KKK.
Sure,
Yeah.
sure.
When the socket waits, that's blocking, right? Or when you let the socket be the delimiter, it's blocking, right? So if it hasn't finished receiving, your call will block until it does.
No, if you pass a size into your receive call, if it receives that amount of data, it will come back, even
Right,
if there's
but if it
more.
hasn't received that much data, it blocks until
So it waits until your timeout.
No,
It waits
that's
for the
not
timeout.
true.
it grabs whatever's there. And
It grabs whatever's there and returns, but it won't grab more than what you've said.
Oh, that's weird.
But if there's nothing there, then it'll wait until anything is there to return. So when you're specifying that 1024, you might get 5 back, you might get 1,000 back, you will not get more than 1024, and you will not get 0 back, because if it times out, it will raise a socket.timeout. Does that make sense?
Mhm.
Any questions on that? All right. So here's where sockets ends and requests begin, okay? Requests is a fantastic library for grabbing anything off of the web. And the reason why I say fantastic is because it's just so intuitively easy to use. I only have one slide about requests, which is what I'm showing you here. Essentially, import requests, and you do request.get. You pass it whatever URL you're interested in getting. If you have any authorization data, you can pass it right there as well. If you have to pass it get parameters, you can pass that through an argument to the get function. If you want to call a post call instead of get, you would call request.post, and you would pass the same data right out there. The thing that you get back is a response. It's stored here as the variable r. You could call r.statuscode, and the status code of 200 means, hey, my response is okay, everything's good, I've got data. Various other status codes are detailed out on the internet. You can look them up. 404 means that the page that you tried to request, the data that you tried to request, wasn't there. 500 means that there was a server problem. There's other codes that say that the asset that you're looking for has moved. It's temporarily unavailable, it's permanently moved, that kind of stuff. This right here, this r.headers, talks about the content type of the data that you've brought back according to the server that you've spoken to, which may or may not be correct depending on who programmed that server. This one tried to claim that the data that came back was JSON data encoded as UTF-8 character set. Again, there's another one, r.encoding tells you that. You could do r.text, and that will get you the human readable stuff from the web page. But because we know this is JSON data, you can also call r.json, and you get a dictionary you get a Pythonic dictionary of the data that was represented as JSON that came over the wire to you. This is a fantastic library and a fantastic, easy way of transferring data, especially from a server like Django or a server like what's the other real quick one? Flask. If you want to pass JSON data back and forth, you instantly have it available to you as Pythonic dictionary.
It's so good that if you're using Python 3, it's in the standard library.
Oh, really?
Yeah.
Okay. Fantastic. Request is in the standard library. All right, so third topic. I'm going to try and squeeze this in because the other two were pretty short. This is the thing that I just researched a ton of in the last 2 weeks. It's called WebSockets. And essentially what WebSockets are is the mechanism that a website like Facebook uses for their chat client, or something like Gmail, so that as soon as you get an email showing up, it's instantly going to show up in your in your email. Essentially, traditional HTML website requests are a request out to the server, can you get me an asset? And then the server responds, and as soon as the server responds, you don't have any sort of connection anymore. WebSockets, however, combine the notion of a socket where you have this persistent connection to a server with the notion of a web asset where you're trying to get an asset from somebody else. So a WebSocket can be used, like I said, as a chat situation. I'm using it actually so that a server can orchestrate sending data out to several different Raspberry Pis. One of the things I was thinking about was this little project that we're working on, this little website for Python Utah North. We could create a WebSocket connection to the server, and then the server can send it live updates of recent poll data or recent vote data to the client, so that it's updated in a lot faster way, rather than having the client re-request a JSON data stream or something like that, because then the server can just say, hey, there's new data, there's new data, there's new data. Found a couple of great libraries in pip. Pip installed Twisted WebSocket and pip install WebSocket client. I'm not going to get into Twisted right now, but Twisted is something we should have a full presentation on at a different time. The most fabulous thing about Twisted is that it is an asynchronous, single-threaded communication protocol for network traffic. And so because it's single-threaded, you don't have to screw around with threads clobbering each other on data. So a lot of the thread safety overhead and nightmare kind of goes away. But with it, because it's only single-threaded, the things that you do, you have to program your code in such a way that it can be broken up into a lot of little tiny bite-sized chunks that you then let the scheduler deal with. Okay, we're going to let you do just a little bit, and then we're going to check for network traffic. We're going to let you do just a little bit more, we're going to check for network traffic. That kind of stuff. So there's a scheduler, and you write your code in little tiny pieces, and then a lot of them, and then and you build them together, you chain them together. They call it, that terminology is called a deferred. I'm going to show an example of a WebSocket server. This is using the Twisted library. This is just a very, very, very simple handshake echo server. Essentially, what this server does is it, at the very bottom, you see it creates an instance of a reactor. The reactor is the scheduler. It listens on a TCP port 9999. Creates an instance of WebSocket factory and then runs. This WebSocket factory maintains a persistent list of users, and then as each user connects, these various aspects of this code run. And you can kind of use this WebSocket library as a foundation for building something larger. You can kind of use it as a base class. But the idea being that in this example, that when a user connects, then that user has an instance of WebSocket handler that is called, and every time we've connected, we have added to a dictionary called users, and it's actually, I believe, where are we doing that? Actually, I'm not seeing it. Can someone see it? It might be defined in protocol. That protocol maintains a dictionary called users. I'll bet that's in the base class, you guys. but essentially what you're seeing here is that the as a message is received on connect or down here on the on message, it iterates through this dictionary of users, and it sends each one of the users a message about the user that just connected. So if you've got 5 users, as the first user connects, that user is going to get a response saying, hey, I know you just connected. Second user connects, both of them get the message, hey, somebody else just connected. Third user connects, all 3 of them get a message. So it becomes that kind of a library. Next topic is the client, WebSocket client. At the bottom, this web-enabled trace is kind of just for debugging, but you're creating WS, a WebSocket app, and that's it comes as part of that library. It's a class that you can inherit from, or you can just use it wholesale. And you're just going to define certain handlers on message, on error, on close, and supply your own functions. And then you just tell it, go ahead and run forever. And then that call will connect to whatever server you're trying to connect to, whatever WebSocket server. And as various events occur, you can respond to those events on message, on error, on close. And simultaneously, you can do things like WebSocket.send. So you can use this foundation to essentially build a WebSocket TCP persistent connection to another server out on the real internet, which is kind of fun. So you build a chat client, or you can build some sort of a content distribution kind of thing. And that's WebSockets. Any questions? It's kind of a bunch of 3 quick little high-level topics. What's up, Chris?
So I'm guessing you use sockets at DuPont?
I do.
Can you just give an example?
Sure, absolutely. So at DuPont, I use sockets in a number of different places. First place is I have a piece of equipment that drives a stepper motor around, and I connect to that piece of equipment using a socket. So I open a socket, establish a connection, and then I send commands to it saying, okay, move this thing over to exactly this position, move it to this position, and then I can tell it to take pictures and stuff like that. So I'm connecting to a piece of hardware with example number 1. Example number 2 is I use a thermal printer to print serial numbers on holograms, and in order to tell the printer exactly where to print the serial numbers and what data, I connect to the printer with a socket.
So the printer has its own software that can handle sockets.
And as part of the printer's publications, they've said, okay, well, if you want to connect in here, if you want to connect, this printer listens on port such and such, and in order to connect, these are the commands that the printer will respond to. The printer is manufactured by a company called Datamax, which is owned by Datamax O'Neill Corporation, and they just have established something that they call DPL, which is Datamax Printer Language, and those that printer then responds to commands issued in Datamax Printer Language. Third example, I have a vision system that's written in C# and a Python management kind of system that sends commands to the C# stuff. The C# we used because it's compiled, it's going to be very fast, very optimal. But the Python code, even though it's slower, is a lot higher level language, so we're able to do the logic a lot cleaner in the Python code, but use the engine of the C#. So even though they're both applications are on the same machine, we run we actually named it Vortex just because that's kind of a ghetto cool name. We run Vortex. It opens up a socket listener. We open up our Python code. We connect to the Vortex code with a socket connection, and then we've established a messaging protocol between the two of us where, in fact, that get image, that was straight from my Vortex code. The Vortex vision system on one of its socket listeners sends me image data. And on a different one, we communicate over with XML data. And we've established that there are certain terminators for data and that kind of thing. So that's a third example of how we use sockets. Any other questions? Well, fantastic. Thanks, guys.
Thank you.
Okay.